Hi, so I recently came across a load of the boards that I designed back in the late 80s, early 90s for the Acorn RISC based home computers, so I thought it might be interesting to have a look through them and see how much I can remember about them. Now this was the first one I did, and annoyingly I don't actually have one of these boards. A while ago I gave away quite a lot of my old Acorn stuff to a collector, and looks like I forgot to keep hold of one of these boards. If anyone's got one, please get in touch. I would actually quite like to have one. And this was the Publicity Leaflet. I've actually got a photo here because this photo was taken sort of before the final production. There's no backplate there, and if you look careful there's actually a chip missing on back there. This was done for Watford Electronics, who are a sort of very big seller of add-ons for the Acorn machines at the time. And this was actually the first third-party hardware product to be demonstrated for the those machines. It wasn't the first one for sale because it took a while to actually get it into production. I don't remember all the reasons. I think there was a long lead time on the HD converter chip, but there were probably other reasons. But so it was actually the first third-party product to be demonstrated at, I think it was one of the computer shows, maybe Acorn user or micro user shows. So here's a photo of the complete board. Now the Acorn machines had a backplane which would take up to 4 standard DIN 41612 connectors. Bus would run up to about 8 megahertz, and these were originally called podules.
A small podule.
And later on, when Acorn wanted to try and make themselves look a bit more business-like, they sort of changed the name, the official name, to expansion cards, but everyone called them podules because that's just, you know, what everyone knew. So and this was the result from quite a lot of the work I did, sort of just really hobby stuff with video digitizers. I built a video digitizer for the BBC Micro and various other things, but these were just like personal projects. I got one of the fairly early Acorn A500 development systems and did a bit of video work for Acorn to use in their show demonstrations and so on, and this product sort of basically came out of that. Again, I don't remember the exact details of how. There were a few video digitizers around sort of on the BBC in early BBC times which tended to be very slow. They used to like work by sort of slow sampling up 1 pixel per line, so they took several frames to build up the image. This is like a full frame real-time digitizer, hence the sort of that being listed in the product info, because that was quite unusual at the time, but certainly at the lower cost end of the market. This used these video RAM chips. Now these were basically like normal dynamic RAMs, except they had a shift register which was the length of the whole row. I think it's 256 locations, and a single read or write cycle could transfer that entire shift register to and from the main DRAM array. And the way I used this was that the video would be shifted into the shift register for the duration of one line, 256 pixels, and then that transfer cycle would be done at the end of the line in the blanking period, so we could get video shifting in at the like 10 megahertz video rate and store it all in real time. From memory, I think there were 4 manufacturers of these, Texas, Fujitsu, Hitachi and Mitsubishi. They all had very subtle differences in their timings and protocols, and I have a feeling one of them, possibly the Mitsubishi, wouldn't actually do the data in. Obviously these were typically used for video display applications where the RAM data will be shifted into the shift register and then be shifted out at video rates. So I was actually using it the other way around, and I think at least one of those chips didn't even support reading data in through the shift register. But I do remember there were timings, and there was quite a few fudge factors to actually get all the chips to work, just because they had slight differences in their timing requirements or protocols or something or other. But I think if you see this board, this is obviously one of my prototype boards that had sort of, I think, Texas, Fujitsu and Hitachi parts populated when I was testing them. The hardware on this was really sort of pretty minimal. We've got a 6-bit flash HD converter. This was a Fujitsu, don't remember the number off the top of my head, but this is a fairly low cost 6-bit converter. We're only running at about 10 or so. There's an inductor there, that's part of a filter to filter out the colour subcarrier, because obviously that will produce aliasing artifacts. So that which is like a notch filter at 4.43 megahertz. Very simple front end circuitry. The analog signal went basically straight into the HD converter. The only things that were added, there was a black level clamping circuit to make sure that the black levels were consistent. Video signals are often AC coupled, so the overall sort of level can sort of drift up and down a bit. If you look up black level clamping, you'll find information on that. And there's also an auto gain adjustment circuitry, and what this did, this actually used an AND gate on the parallel output to produce sort of signal when all the output bits were 1. Then you would use that to increase the upper reference voltage of the A to D. So the A to D's reference voltage was between the black level of the analog signal and the peak of the video. So regardless of scene content, it will try to adjust itself so that the full range of the A to D digitized that scene, which it was a disadvantage for certain things like measurement where you actually wanted to know absolute levels, but in most cases it meant it optimised the contrast, and with only 6-bit per pixel, you really needed that to get a nice sort of contrasty image. This chip down here, this is a LM1881, which is pretty much universally used as a sync separator for analog video. The clock oscillator, this was actually an RC oscillator. The reason for using that rather than something like a crystal is that you could start it on the start of each line very consistently. With a crystal oscillator you need to use a phase lock loop, which is a lot more complicated, whereas this, if you simply start and stop the oscillator based on the sync, because it's got virtually instant start time because it's just an RC oscillator, it means that you could get good synchronization between the horizontal sync and the pixel clock, and this was just a multi-turn part, so you could sort of manually adjust it to get it effectively controlled the width of the image that you were digitizing. There was one PAL on here and a couple of other HCMOS chips which just generated the timing signals for the DRAM. This was very much software controlled. It hogged sort of most of the processor when it was actually digitizing, sort of disabled interrupts and did all sorts of other nasties. And this wasn't transferring from here to the bus, it was simply controlling the timing of transferring the video data into the shift registers of this VRAM. And then once that grab had taken place, the processor could then read the data out from this RAM at its leisure. I think this was 512 by 256 pixels, 6 bits per pixel. Each of these held 4 bits, so on 2 of these chips only 2 bits were used. The ROM here just controlled the software. One nice thing about the Archimedes series is that both the drivers and even the application software could actually be stored in the ROM, so you just plug the thing in and it would just start working. You didn't need to load any additional software at all. Just a couple of bus buffers. System address bus was driving all these 4 RAMs as well as this EEPROM, so that was just reduced the bus loading. This worked sort of pretty well. I don't know how many they sold eventually, but for quite a long time it was the only video digitizer available. Produced lots of nice demos and stuff with this, because video and sort of captured images on home computers was a pretty new and novel thing in those days. So if anyone actually has one of these, please get in touch, because I would actually like to have one. Some of this is a little bit deceptive, because a lot of these images, for example, when I was doing some experiments using red, green and blue colour filters to do multi-frame captures of colour video, somebody did actually produce a second board which was like a colour multiplexer, where you could actually take a colour signal and feed it through their board into this, and it would also make the process of the doing the colour digitisation. And there's sort of various software provided for just sort of demos and so on, but it would actually just plug in and work. So this is on the later version of the operating system, the RISC-OS 3, I think. The earlier versions you had to sort of load some software in and do sort of command line stuff, but on the later, once they got to the full sort of desktop environment, then this would just appear as a little icon on your desktop, sort of click it and away you go. Practically speaking, this will capture one field sort of video signal. It's 50 Hz field rate but 25 Hz frame rate, because it's interlaced. Now you could select whether you wanted an odd or even field, but this would only grab one field, which wasn't a big issue because the Archimedes didn't really support interlacing properly, so its output video resolution was I think sort of 256 by 640 in the highest resolution mode, so interlacing and capturing full frames wasn't a particular issue. So you could do it, but you couldn't do it in one go. You'd have to capture one field and then you'd have a slight delay while you read that out before you could capture the next one. But so that at the time that wasn't particularly important. The actual capture stuff, as I say, that was all done in software with some sort of very tight, highly optimized assembler, just sort of doing a lot of the timing in software across the bus just to generate the timing signals for the RAM. Now, one board I do have, this is actually a custom version I made for a company that was making a very early sort of audio visual effects system, which would sort of do like real-time video effects based on audio and MIDI input. And the difference is, although it's based on that design, but it had a bit more autonomy. This could actually do a full frame grab without any interaction from the processor, because that system was using Ethernet networking. We needed all the interrupts to carry on working, so this had a bit of extra hardware. There's an extra PAL on there to handle the actual transfer of the data into the video RAM by itself, with minimal interaction from the processor. There was also a PAL here, which is a lookup table, so you could have a few different palettes on the digitized input before it went into the video memory. Right, here I've got a selection of various memory expansion boards. So these were for the 300 and later the 400 series, and they were very much sort of fixed in how much memory they could take. I don't think any of them had socketed memory. I think the baseline level machine was 0.5 megabyte, and 4 megabytes was the top end. So these expansion boards basically plugged in to the processor and memory controller sockets using these. These are actually originally made by a company that made in-circuit emulators, and they were sort of quite expensive because they're only made in small volumes. And these ones, I think there's a machined PCB stuck to a sort of plastic. That was the original manufacturer. And later on, the guy that ran one of the other companies that was in the Archimedes sort of peripheral business, his father was an engineer, and he actually made some special tooling to sort of take this, I think this is the standard SRBP PCB material, and like simultaneously cut the tracks to the right depth and then glue them around these blocks. So those were a bit cheaper. Again, I don't quite know the point at which we changed over from using these. At that time I wasn't really involved at all in the manufacturing side of things. That's what Watford Electronics handled that themselves. So I think these two were for the 300 series, the 2 meg and a 4 meg version. These are using zip packaged memory chips, which were again quite popular at the time, so you could get very high density on through-hole PCB. The surface mount was a bit of a new thing then, so very few people were using that. And there's a connector here which goes back to pick up the data bus from the processor. I'll see if I can find a photo of that and drop that in. So the idea is that you unplug the memory controller from the motherboard, plug it into this socket, and then this will then plug back into there. There's a power feed that came from the power connections. We probably could have taken power from these pins, but just because this memory was quite power hungry, wanted to get some a more solid power connection, and so there was a ribbon cable and then another plug-in board that plugged into the. Actually, I think on these ones plugged into the video. That was right. The video processor had the data bus, and the memory controller only had the address bus. So we needed to tap into both of those to get the full address and data bus that we needed to run these. There's not much in the way of logic, but we did use a PAL for this. The PALs were quite popular in those days because it made it a bit harder for people to copy the design. I mean, it's not impossible, but it added, it means that people couldn't just a simple clone, because there were times when that sort of stuff was going on. There were sort of people ripping each other off with their designs. One additional thing though I put in there, which I think was unique, there were quite a few companies making different memory upgrades, but I don't think anyone else did this, was the ability to software disable the expanded memory, so you could effectively downgrade to what the original machine's memory was with a software command. The reason for that was so that people like software developers could check that their software would run on the lower end machine. Say that at that time there were machines out there with 0.5 meg, 1 meg, 2 meg, 4 meg, and one of the quirks of the memory controller is that it had a fixed number of pages, and the page size depended on the amount of memory installed, so that a 4 meg machine would have a different page size to a 1 meg machine, and this made it quite difficult to predict how much actual memory you'd have available in any particular circumstance. So these boards could actually be software downgraded, but there was a slight extent to which that backfired, in that a lot of customers, we advertised this as a feature, software downgradable to the original spec, and a lot of customers didn't quite understand why they'd want to do this, and thought, does that mean there's some compatibility problem, you have to sort of disable it? So that was a slight backfire of a feature, but I don't know how many people actually used it, but it was just, I thought it was a potentially useful feature. And these are sort of the ultimate development in this sort of series. These were for the 400 series machines, which came as standard with 4 megs of RAM and couldn't be upgraded, but there was a higher end machine called the 540 which could take up to 8 meg of RAM. It used a board with an extra memory controller and extra memory. So these boards actually did two things. Firstly, they provided the extra memory controller. So again, this plug goes into the main board, this is the first memory controller, and then this is the second memory controller. Have I got any here that actually got any RAM on them? So this one's actually got the memory, and these are in SIP modules, rather like the Sims that you see even to this day, but these have actually got pins on them which go into these turn pin sockets. I don't know if we ever actually soldered these direct. Obviously these are all prototypes, so these are all socketed, but again these have the advantage of slightly higher density. You can get high density on these than you could with Sim sockets. The other thing these did was provide ARM 3. Now the ARM 3 was a sort of faster processor which came out sometime after the original machines, and because they were designed so that the core was asynchronous to the bus, you could basically upgrade the machine by just plugging a board in that had this processor on it and a clock, and the core would run at 24 megahertz, but it would synchronize with the 8 megahertz system bus. Again, I did a board for that, which again I don't actually appear to have one. I've probably got a photo. I'll stick that in if I can find it. But these boards combine the memory upgrade with the processor upgrade. So there's this board that sort of plugs into this connector here, so you could have a simple memory upgrade and just put the original ARM2 processor on a board that plugs into there, or you could have the combined memory and ARM3 upgrade using this ARM3 board. Because it's plugged into the processor socket, this didn't need the cable back to the video controller because we've got the full address and data bus available on here, so this is just a single plug-in board. So this was actually, this one was for the 300 series, so this was basically 4 meg RAM plus ARM3, and this was for the 400 series, which is 8 meg RAM. There's actually two of these because there were, at some point Acorn did a slight board revision on the 400 machines, so the only difference between these is there's about some like a sort of 5mm difference between the positioning of these sockets, so we had to do another board just moving these around a bit to so they'll actually plug in. The other thing that's on here, this was purely for personal experimentation and never intended to be any sort of product, but bear in mind this was in the day where like 4-layer boards were really expensive to get made. But this is for the coprocessor. The ARM system architecture had a facility to add a hardware coprocessor, which basically used the a special coprocessor bus on the ARM3 processor, and that worked by sort of basically sniffing the execution bus and executing instructions as it saw them appearing on the bus for floating point expansion. But I was quite interested in using this for high speed, for example video capture, just using it as very high speed I/O. So I think I did actually get something up and running on this, but that was very much like a hobby project. This was never actually used in production. So I think this sat underneath the floppy drive, so the floppy drive would have got in the way of actually using this for a product. And again, all of these had this PAL on here for the software downgrade. The 8 meg had some extra logic on here, I think, to do with address decoding between the two memory controllers. It is possible that not all of these things actually made it into production. I really can't. It's so long ago, I can't remember how. I remember we did quite a lot of variations. I think most of them were actually manufactured, so I didn't have that much contact with the production side of things, so I wasn't always completely in the loop. So that's 1990, this version. Which was the date on this one? 89 for this one, and the 8 meg. So actually I was surprised it's that early. But adding to and expanding the machines was a very, very popular thing at the time. The original BBC Micro had lots of expansion ports, and the Archimedes machine similarly had lots of I/O, and it was something that users were very, very keen on, the expandability. So there were hundreds and hundreds of boards made for all sorts of different things. So lots of things like memory, lots of people did them, and there were quite a lot of other more specialist add-ons produced over time. And I have a feeling these were probably the first 4-layer boards I ever designed as well, because obviously we needed a nice big power plane for all this memory. And all these PCBs were designed with software I wrote myself that ran on the Archimedes, which was this is in the day when like professional PCB software was very, very expensive, had to run on very expensive workstations. So I sort of wrote my own software that evolved over a few years to be sort of fairly usable. Compared to today's software, it's pretty limited and a bit of a pain, but it did the job. And this is also back in the day where I think I actually outputted vector data into the Acorn Draw program, which is like a vector-based drawing program, then exported that as a PostScript file, which I then sent to my local typesetter to produce typeset films that actually got sent to the PCB manufacturer. So next up, this is the Scuzzy Card that I designed for Oak, I think then Oak Computers, then became Oak Solutions. They specialised in doing sort of external hard drives and storage hardware, and then moved into networking after they merged with Software Solutions. Incidentally, all the Archimedes machines were very popular in schools. The schools had a lot of BBC Micros in, and then the Archimedes was the sort of natural successor to that. So there's a lot of interest in networking and school classroom type applications. Now I think possibly slightly earlier than this, Acorn did actually do their own Scuzzy Card, but it was very expensive and sort of rather complicated. It had like onboard sort of buffer memory and used quite an expensive controller. And sort of the primary aim from this was faster, larger hard disks. At the time, the standard hard disk controller, either built in on the 400 series or as an extra add-on for the 300 series, was based on ST506, which had sort of some inherent limitations in terms of speed and also disk size. And so around that time, Scuzzy drives, high capacity and generally also faster. So this was really designed just as a way of getting more storage, quicker storage on these machines. Sort of relatively simple design, but it's got a few interesting quirks. It's using a standard NatSemi 5380 Scuzzy controller. I think that was just literally the cheapest Scuzzy controller around at the time. Very simple device. It's got the hardware line drivers and stuff, and it's got a small amount of logic, but there's no sort of buffer memory or anything high level like that. And we actually operated this in a 16-bit mode, so we used the 16-bit bus on the machine, and these are just some latches so that we could actually transfer 2 bytes at a time in each direction, which gave us sort of quite a decent amount of speed. But also I did some tricks with the bus interface, the backplane bus interface. So it was an 8 megahertz 16-bit bus, and there was a mechanism in there for clock stretching so that you could have different speed peripherals, and the peripheral would provide a signal to synchronize it so that it could optimize the speed of transfer, so it would go just as slow as the board needed. And the way that Scuzzy works, it uses like a request acknowledge system, so that when, for example, if you're reading, you'd send a request, the peripheral would acknowledge it, and then you sort of drop the request, then the peripheral would drop that. And I basically tightly coupled that in with the backplane bus's pulse clock stretching. It basically took advantage of the fact that all Scuzzy drives had at least one sector, 512 bytes of buffer, so that when you tell it to read a sector, when you get the first byte in from that sector, the rest of it would come very, very quickly if you could handle it. So what this did was it actually used this bus stretching on the bus, so it would read the first byte, and when that first byte came in, it would then sort of, I don't remember the exact details, but basically it would lock the request acknowledge cycle to the bus cycle. So it was actually using the system's own bus control system to do the handshaking right through to the Scuzzy side of things, which meant it was very, very fast. Certainly at the time, this was the fastest hard disk interface. I think something like 1 megabytes a second average sustained transfer speeds. There's a couple of pals on here. Once we figured out the whole, the 16-bit and this handshaking thing, everything else was sort of relatively straightforward. Again, we've got the ROM on here that had all the software committees. The RISC-OS operating system had all the hooks in to provide alternate file systems. So literally, your interface simply, read sector, write sector, and it would take care of all the file structure side of things, so that it was relatively simple to add a simple block read-write device to it. You didn't have to write your own file system. All you need to do is provide the low-level routines for reading and writing sectors. There is some hardware on here which was to provide a timeout, so if something did go wrong with the Scuzzy handshake, it wouldn't leave the machine bus hanging indefinitely. So there was some timeout hardware here, but I don't recall that ever being a particular issue. It's just things like, for example, if the cable comes out or something, it just prevented the machine completely hanging and crashing in that situation. But this was pretty successful. There were a few other third-party Scuzzy interfaces. I can't remember if this was the first sort of third-party one apart from the Acorn one, but it was sort of fairly early on, and because it was fairly low cost, because it didn't have any buffer memory on board, which is a lot of the other competitors did. It was sort of significantly lower cost, and I think sold a pretty decent number of these over a few years. And this was an Ethernet interface, again also for Oak. This was very heavily targeted at education. The Archimedes had a built-in networking system called Econet that ran over RS485, and this dates back from the BBC days, which it worked quite well. They had quite a lot of software support for like file servers and print servers and so on, but it was quite slow. For something like BBC Micro, it wasn't a big deal, but once you get up to these sort of faster machines, the speed of the networking was very much a limiting factor. Now again, Acorn did their own Ethernet interface, which was again quite a bit more complicated than this, and it had like full network stacks or TCP, IP and all that sort of stuff, whereas the aim of this was really, faster Econet. I think eventually TCP, IP and all that sort of stuff was implemented, but this didn't use that. What we did is we actually had an allocated special Ethernet frame type, and we used to just simply encapsulate raw Econet packets within that, and the interface to the operating system actually pretended to be Econet, so any application that was written to run over Econet would run over this with no modification. It was just an awful lot faster. So it's just really almost like a hardware replacement for the Ethernet. But again, bear in mind in those days, internet wasn't really a thing. So pretty much the only use for the Ethernet was to link these machines together. It wasn't really even used to link the Acorn machines to other machines. It was purely a fast sort of classroom networking system, and Oak Solutions did their own file server software and other support for to make this a package. And there was also some functionality in here to use some non-volatile memory just to make a few things non-volatile within the machine. So for example, you could set it to boot up straight as soon as you turn it on, and there's a few other things which I don't remember the exact details of, but there was a little bit of software functionality in there that was very useful in that context. And I think we actually even did a board which had just literally an EEPROM and the non-volatile memory on it for those applications that were using Ethernet to do some of the same things. Again, I don't remember exactly what, but there were a few things which made quite a difference to the usability in a classroom setting, just having this extra few little bits of software in the ROM and a little bit of non-volatile configuration memory. This is based around a Fujitsu MB86960 Ethernet controller. This had a 16-bit interface, and we used that to get the maximum bus throughput. Again, speed was really just the prime requirements. Let's just get this thing running as quickly as we possibly can. No TCP protocol overrides anything, just raw frames. And of course, this was before the days when 10BASE-T was around. So the normal network interface was coax. 10BASE-2, otherwise known as ThinNet, which was literally an RG58 coax cable connected with T pieces to all the machines and a terminator at each end. This was isolated from the machines for safety reasons, so we had a DC to DC converter, transceiver chip and a pulse transformer to provide the data isolation. And this also had what was known as an AUI interface, which was to connect to other physical Ethernet systems. The common one was known as thick wire Ethernet, which used like great big thick sort of half-inch diameter wire for longer distances, and also you could also use this for fibre. I don't think this interface was really used very much, but in terms of cost, the only additional cost of providing this interface is of the socket and some links to select which interface. So I don't know whether this actually got used much at all. It was pretty much a classroom full of machines on thin wire Ethernet. A fairly early Ethernet controller, so it doesn't have any packet buffer memory on board, so it needs these external SRAMs. And this was just a very straightforward bus interface, so again there's very little logic needed to interface this to the rest of the system. And we also did, this is a version for the later A3000 machines. This was like an internal card that just plugged down onto the main board. There wasn't like a proper bus expansion system. There was just like a bunch of connectors so you could put one card in. And because that was only an 8-bit interface, we just used, there's only one RAM here because we were just using an 8-bit bus interface instead of 16-bit, so it was a little bit slower. And we didn't bother with the AUI interface, so it's just thin wire Ethernet only. Right, this one's a little bit more obscure. The Acorn people will probably be a bit less likely to have heard of this. This is a Teletext receiver card. This was almost exclusively sold into schools. The original BBC Micro had a Teletext interface, and at one point the BBC sort of cooperated with Acorn to provide a service where you could actually download software over Teletext. But also it was used as a sort of an information service, obviously again very much pre-internet. This was done in conjunction with a company called XOB, who are very much into educational software. I wrote a BBC print server for them as well, for sort of classroom applications, and also some Ethernet hardware, sort of lower cost Ethernet boards and boards with built-in clocks and so on. So we're sort of looking at, how do we do teletext on the Archimedes machine? From what I remember, the original BBC Micro teletext unit was used basically a standard TV teletext chipset with sort of dual porting of the memory, so it could request a page and then that page could just be copied into the Micro. This works slightly differently. I was sort of looking around for sort of chipsets. TV teletext chipsets tended to be quite highly integrated. But I actually found this is actually part of a 2 chipset made by Texas Instruments. It's a CF72305, and this literally just does the analog data slicing part. So it takes a video signal and produces like a clock and data out and sync signals that you can, the companion chip to this will then decode and produce sort of dual display stuff. This was never actually a chip that TI sort of advertised or sold directly. I found these in CPC, who were a company that specialised, particularly at that time, in TV spares for TV repair companies, and they sort of stocked this chip. So I'm not sure, I think we maybe made a couple of hundred of these, but I ordered these from them. Effectively, they were like spares for TVs rather than sort of through the normal chip supply chain. I imagine the numbers are probably too small for anyone to notice that they were selling sort of lots of these one part of a two-part set to a repair company, but we managed to get them. But I remember when I tried to actually get these through like TI distributors, they didn't even know it existed. So this actually used this tuner. This was actually there was a company that specialised in end-of-line surplus components for TVs. I think they're in Southend or somewhere. I don't remember what they were called. And this was just like a surplus batch of TV tuners. I think maybe a couple of hundred of them. And this was a very standard sort of tuner that you'd find in an analog TV of the era. It just takes the UHF in. This one's using a surface acoustic wave filter, which was pretty much sort of standard in those days, and it produced the video out, and it needed an analog tuning voltage, 0 to about 33 volt tuning voltage. To add to the usefulness, I actually added a sound demodulator on here, so you could actually use this as an audio and video sort of sound source. So for example, you could plug that into a monitor to use as a TV, or you could feed the video into a video digitizer for capturing frames. Video capture wasn't really a thing in those days, but this chip was really cheap, so I thought it made sense to add that just to give it a little bit extra functionality. So we've got this analog sort of data slicer chip. This will produce the low-level digital data extracted from the video signal, and then there was some various sort of timing functionality on a 7202 FIFO from AMD. So it would I think there's a GAL there. I think it's an ICT peel device for that one. So these would just turn that serial data into a parallel stream, do all the various timing synchronization stuff, and shove that data into this FIFO memory, and then that would then get read out under interrupts to the computer, and then all the further decoding was done in software. There's actually a bipolar PROM on there. This was just to provide enough memory for the operating system to recognise that the device was there, so that the software could find out which slot it was plugged into and identify it. There was no software or anything in there because you needed the external software to do anything useful with it, and there wasn't really space for any PROM on here. 2 GALs and a peel. I think one slightly sort of thing of note is there's almost every different size of dip on here. There's an 8, there's 14s, 16s, 18s, 20s and 24 pin dips all on the same board. And one slightly sort of interesting thing in it here was because this tuner needs an analog tuning voltage, so 0 to 30 odd volts. At the time, D2A converters were really expensive, and it turned out the cheapest way to do a D2A converter was to actually use a PIC 16C54 to generate a pulse width modulation waveform, which was then filtered to provide that tuning voltage. It also provided an interface to this non-volatile little E squared PROM, which was used to store the tuning settings for each channel. But the prime function of that PIC was just simply to act as a D2A converter for the tuning voltage. And from memory, I think there was maybe only a 5 volt supply available from it. There's a voltage regulator here which supplies the tuner. I think that maybe either there wasn't 12 volts available on the backplane, or there wasn't on certain machines. Again, I don't remember the exact details of that, of why that's there, but I think it may have been the case that there was only 5 volts available on the backplane. But one big advantage of this system, because we were doing like all the decoding and everything in software, we could actually stream every page that was coming across in real time. So we could build up a database of the entire transmitted teletext sort of database within sort of one page cycle. And I think XOB did their own teletext server software, so you could actually have one of these on a machine on the network, and then any machine anywhere on the network could access the teletext pages. Digging through some in my dim and distant memories, so I don't remember all the details. If anyone does or has any memory of this stuff, please stick it in the comments. It would be interesting to find out. So these were the sort of most of the products I did. I did loads of other stuff, things like floppy interfaces and slightly different memory boards. I was looking at the dates on these boards. I was almost amazed at how much stuff that I was doing at the time. And I think I actually had a full-time job as well when I was doing all this stuff. But it was quite a nice business for a while. Quite an interesting sort of fairly tech-savvy community. I used to work at a lot of the computer shows demonstrating stuff, sort of having chats to users, which was sort of quite interesting stuff. Then it was just sort of gradually petered out as the PCs took over from the Acorn machines. But in their time, there were things they could do, things like the machine with a video digitizer was, compared to the PC solutions, it was a much cheaper and much slicker system at the time, but unfortunately it all got taken over by the PC world. So while I was looking for photos of some of these boards, I actually found this. Now, As far as I know, this is actually unique. I'm not aware of anyone else that did this at the time. This was really just an experiment. It never went anywhere. It was just really a sort of thing I was playing around just to see if it could be done. The memory controller on the Archimedes actually had 2 DMA channels. One of these was used for video and one was used for sound. Both the video and sound were handled by the video controller chip. So this was just a prototype of an idea I had of whether you could actually drive 2 monitors off the same machine using the sound DMA channel to run a second video controller. Yeah, I'm pretty sure this did actually work. I don't remember whether you could get the full resolution out of both monitors. There wasn't really any sensible application for it, and I think mechanically it would have been quite difficult to fit this into a machine and actually get the connections out just because of the mechanical constraints. Don't think I even ever sort of talked to anyone about sort of productizing it, say, because it didn't really have an application, and the way the software operating system architecture worked, it wouldn't have been that easy to. Obviously, there's no multi-monitor support in the operating system, so it was really just an exercise to see, is this actually possible? And so the answer was yes, but it wasn't actually all that useful. So it was interesting to see how sort of looking through this brought back some memories. If you've got any memories of this time, the old computer shows or stuff, please stick it in the comments. Be quite interested to see what people remember, and say if anyone's got one of those video digitizers, I would actually quite like to have one. So get in touch.